Hi everyone. Today we're going to look at thermal energy, and we're also going to look particularly at two ideas. One is called thermal expansion, and the other is called thermal contraction. If you need to get a hold of me, my email address is on the screen. It's rcrawford@jcpsmail.org. Here we go. So when we talk about thermal energy, I just want to briefly go back and make sure we still remember the definition for energy that we're using in this class. And for me, I think the best definition is energy is really just anything that can move or change matter. So if you see matter, if you see something moving, energy did that. If we were to be able to look at particles, um, or atoms, and we see movement there, once again, energy did that. So motion and change are generally caused by energy, and that's the best way to define energy. Energy, of course, is not made from atoms. Energy is not matter, it's not physical stuff. And so, in many ways, energy is the opposite of matter, and matter meaning anything that's made of atoms. Now, we did say that there are two categories of energy early in the year. We have potential energy, and potential energy is energy that we have stored in an object or in particles, so it's stored waiting to be used. And then we also have kinetic energy. Kinetic energy is energy that is already in motion. Okay, so we have several different forms of both kinetic energy and several forms of potential energy. Forms really just means type. And I want you to think of potential and kinetic as two categories with several forms or types of heat. So let's go ahead and talk a little bit about thermal energy. Thermal energy is really just the form of kinetic energy that we find in the random motion of all particles. Clearly here, I'm showing you something that is a solid. We know that because the particles are vibrating in place, they're locked into place, and they are not moving around. So whenever you see particle motion, that's what we call thermal energy. The way I really like to think of it is I call it atomic jiggliness. I don't know why. It seems silly, but it's also memorable and it really gets to the heart of what's happening at an atomic level. I do want to point out that all atoms are always in motion, and so all stuff has some thermal energy. The complete absence of thermal energy would be something called absolute zero, and really that's not a thing that we're able to achieve. Okay. So when we look at thermal energy, it's very natural for us to talk about heating and cooling things. So if I were to take a cube, a copper cube, and I were to cool it, right? So if I were to some way lower the temperature, if you want to think about it that way, whenever I cool something, I'm going to find that the atoms, they're going to like move less. They're going to move slower. And as a result, they're not going to collide as much. So they're going to be able to move closer together. Okay. Now, if on the other hand, I take this same copper cube and I add some heat to it, so I give it more heat, then these atoms that make up the copper cube are going to become more jiggly, right? They're going to have more motion. They're going to move faster. They're going to collide with each other. And these collisions are actually going to push these atoms further apart. So when we heat things, the atoms move faster and they move further apart. When we cool things, we find that the atoms move slower and they can once again move closer together. Okay. Now, this gets to the heart of what causes thermal expansion. So thermal expansion is really just this idea that when we heat an object, it actually gets slightly bigger. And by that, I mean, if I heat this copper cube itself is going to increase in volume. It's going to take up more space. It's going to get slightly bigger. Now that change may not be noticeable to us in something like copper, and this it getting slightly bigger is completely tied to the fact that its atoms are moving further apart. So of course, if the atoms move further apart and the atoms are what make it up, it's going to take up more space. On the other hand, we have thermal contraction. Thermal contraction is just this idea that, as those atoms move closer together, that this copper cube, if we cool it, is going to get slightly smaller. Okay, and so we can see down here. This is it's a good example of really what's happening in both thermal expansion and thermal contraction. Now, while this is an interesting idea, this turns out to be quite important if you build things. Okay, so I don't know if some of you will undoubtedly have noticed these on the roadway. You often find them on bridges or any place that you have big expanses of either concrete or asphalt. They're very common on bridges as well. If you've never seen one, if you've driven on the interstate, you've probably heard one. If you've been on the interstate and you suddenly heard a dun 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 dun, that rhythmic and repetitive thumping noise, that usually means that you're driving on a section of highway that has these things on it, and these are called expansion joints. Okay, so the idea behind an expansion joint is an expansion joint is going to allow the roadway itself, the road, to expand and contract. Okay, so thermal expansion joints are really about expansion during the summer when it's hotter, right? Because when we heat things up, things are going to get slightly bigger, and it's going to contract in the winter. And so I want you to notice how these plates here. So this is like a space that was left in the roadway, and we can see that here in the summer, notice how the crack that is in between these two sections of the road is very small, right? Because it's thermally expanded. But in the winter, we're going to find that the road has contracted, and you're going to see that the gap is much bigger, right? Because the road has physically gotten smaller. So I want you to like think, okay, so you may be like, well, why do we need to do that? Why do we care if the road expands? If we were to install these big sections of road and we did not allow for it to expand and contract, this is what happens. The concrete will, or the asphalt will literally swell to where it's under so much pressure that it will literally just buckle and bust. And so this is a section of roadway where an expansion joint should have been installed, but it wasn't, and the road began to expand and then it burst. Now, it's not just roadways, and this is something you can try at home. If you have a balloon at home, you can take that balloon and put it in the freezer. I hope some of you will choose to do this. And so when you put a balloon in the freezer, we're going to be cooling it, right? And the air inside, the air particles, the air molecules inside that balloon are going to be able to move closer together. As a result, it's going to seem like the balloon is not as inflated as much. It's going to look like the balloon has lost some of its air, when in fact, what really happened was the particles got closer together. We can, of course, can reverse this. And so here in the picture, we're pouring a very cold liquid called liquid nitrogen over the balloon, and we can see that the air inside of it is contracting very, very quickly, right? But now, if we let that balloon warm back up, we can see that the balloon will, as the particles warm back up, they begin to get further apart again and they begin to expand. So, this is something that we can see. Thermal contraction and expansion are something that we can see really just all around us. It could be maybe you have a door in your home that during the hot summer months, maybe that door is hard to open or close. Maybe it sticks a little bit. That's usually because of thermal contraction. Can be for other reasons, but a lot of times that's thermal contraction working. All right, guys, I think that's going to do it for today. So I hope to see you guys tomorrow. Good day.